welcome to Virtual Laplace class. In this video, we're gonna introduce the concept of Laplace transform theorems. In the first place, let's take a quick look at what Laplace rules and transform is. That will really help. Here we evaluate some of Laplace transform functions by formulas, like Laplace transform of a constant function, exponential function, trigonometric function, and so on. On the other hand, we could examine Laplace transform summation due to linearity property of Laplace transform, which would be the summation of Laplace transform of the functions. Look at the example. It reminds you that the Laplace summation of two functions would be the summation of Laplace of those functions. Let's consider a multiplication of two functions. So what would be the Laplace transform product? Can we set a formula or can we use the other patterns we had before? The answer is yes. And here comes the Laplace transform theorems. These theorems are those famous patterns and formulas that you're supposed to memorize, and they consist of instructions added to Laplace's formulas, which makes it possible to evaluate the Laplace transform of other functions, for example, multiplication, derivative, and integral. The first theorem is called shifting theorem or theorem of transfer on the s-axis. Here, there's a paramedical function for you. Look at the Laplace of e to the at times f of t, and certainly you pay attention that it is the multiplication of two functions. I put e to the at away and just evaluate the f of t, and according to the existence of e to the at, I apply an action to this function. I turn s to the s minus a. So the Laplace of e to the at times f of t is equal to capital F of the s minus a, which f of s is the Laplace of f of t. I have a couple of examples for you. The Laplace of e to the 2t sinus 2t. So I use the shifting theorem. E to the at is equivalent to the e to the 2t, and the sinus of 2t is equivalent to the f of t. First of all, I evaluate the sinus of 2t according to the shifting theorem. That would be 2 over s to 2 plus 4. On the other hand, I turn all the s in the Laplace transform to the s minus 2 according to e to the 2t. That the answer would be 2 over s minus 2 to 2 plus 4. So you see how easy it was. Look at the second example to make it more obvious. The Laplace transform of hyperbolic cosine 3t times 2 cosine 2t. This is a different and kind of good example. You may ask yourself, why do we have this example here? You know why? Because you can turn hyperbolic cosine 3t to an exponential function and write it in this form: half of the e to 3t plus e to negative 3t. So this is the form that hyperbolic cosine is known as. Then I multiply the hyperbolic cosine 3t to cosine 2t, and according to Laplace linearity transform, it is the half times out, and as you see, cosine 2t is multiplied to the parenthesis. I go ahead. Actually, here you can see that it is the linearity Laplace. Also, there is a summation of these two functions. So Laplace will affect on both functions. It is equal to half of the Laplace e to the 3t cosine 2t plus the Laplace of e to the negative 3t cosine 2t. Actually, you know the Laplace of cosine 2t. I'll write it here for you. It is s over s squared plus 4. Here it is. The function exactly turned to the shifting form. So I just need to evaluate the Laplace of cosine 2t. that I've just done that you see here. Then I turn s to the s minus 3. If you remember, I've said that before, it is because of e to the 3t function. Here you see the answer. The Laplace of e to the 3t would be s minus 3 over s minus 3 squared plus 4. The Laplace of this function is also the same. The Laplace of cosine 2t would be s over s to the 2 plus 4. And again, I turn the function in term of s to the s minus the negative 3. So I will combine these two negatives. The answer is s plus 3 over s plus 3 squared plus 4. I'm actually going to talk about the second Laplace theorem with the term of differentiation theorem. If we have the Laplace transform of a function like f of t, the Laplace of f of t is just going to be the capital F of s. So the left-hand side of this equation would be the same as what we did with shifting theorem. Firstly, I put t to the n away, and actually I'm going to do this multiplication Laplace by parts. I evaluate the Laplace of f of t, which was going to be the capital F of s, and afterwards I multiply negative 1 to the n and the n derivative of capital F of s. So the Laplace of t to the n times f of t would be 1 negative 2 the n times n derivative of f of s. Look at this simple example. For the Laplace of t times f of t, you just need to put n as it is equal to 1. Negative 1 to 1 is negative, and the first derivative of f of s is f prime of s. So look at this example, the Laplace of t times sinus t. Can you tell me which part is equal to f of t? Yes, you're right, sinus t. The Laplace of sinus t would be 1 over squared plus 1. Now, what's going to happen here? I just have to evaluate the first derivative of sinus t, as you see I've already done, then multiply it to negative. And I finally reach to this form of function. But look at here, it is the multiplication of three functions. Sometimes you have to evaluate the Laplace of three multiplied functions instead of the product of two functions. This pattern is a combination of those two theorems I mentioned before. In this case, you have to start evaluating the Laplace by the innermost function, and in each step, you multiply the given function to the previous function, and finally, you will evaluate the Laplace. I'm gonna follow this pattern. So initially I will evaluate the Laplace of cosine 2t. As you see, it is the most in a function. So it will be s over s squared plus 4. Now I have to move one function back, and I'm going to evaluate the Laplace of e to the negative t times cosine 2t according to the useful shifting pattern. This is equal to the Laplace of cosine 2t, then I replace s to the s plus 1. So this would be the result. And again, I move one function back to find the Laplace of t times e to the negative t times cosine 2t. And as you know, the derivative theorem shows up. So I have to find the Laplace of t times f of t. And I use the same pattern. Here is t, and here you got f of t. Here you see the Laplace of t times f of t is negative f prime of s. Here is f of t times e to the negative t times cosine 2t. So what is the Laplace form? It is written here. Finally, I take the first derivative of this function and I multiply it to negative. So we can see the result. The next important theorem is Laplace of integral. If the Laplace of f of t was equal to the right-hand side function, can you guess what the Laplace of integral from 0 to t f of x dx would be? pay attention. In this case, first of all, you have to evaluate the f of x, which is equal to the capital F of s. And you see 1 over s multiplied to the f of s. The reason for that is the integral, as I said. Nevertheless, I want you to consider on this example the Laplace of integral from 0 to t hyperbolic sinus 4x dx. First of all, I evaluate the Laplace of hyperbolic sinus 4x. That would be 4 over s squared minus 16. Now, you either assume that here comes the integral from 0 to t, and according to the integral theorem, the answer will be multiplied in 1 over s. And in conclusion, I will introduce the integral Laplace transform. You see, the integral Laplace transform. Let me tell you how it is like. If the Laplace of f of t is equal to the capital F of s, and the limit of f of t over t, as you see t approaches to 0, is equal to a, the Laplace of f of t over t will be like this. If you consider on this function, you will realize that in this case, you take the Laplace of the denominator, I mean f of t, and because of the t in the denominator, I take integral of the whole answer from s to the positive infinity, so the Laplace of f of t over t would be the integral from s to the positive infinity of f of p dp, that the f of p is the Laplace form of f of t. Please give most of your attention on the previous theorem and this one. These two theorems are the same exact opposite, in the way that the first theorem is Laplace of integral and the second one is the integral of Laplace. And as you see, I take integral of this Laplace. Another example here, I want to take the Laplace of sinus t over t. And according to the fourth theorem, initially I evaluate the Laplace of sinus t, and it is 1 over p squared plus 1. And I will take the integral of the answer because of this t in the denominator from s to the positive infinity. We assume that you memorized or looked at the famous integral formulas, so I ask you, what is the derivative of 1 over p squared plus 1? Here you see the answer is inverse p tangent. To find the third answer of the integral, you have to place the bounds from positive infinity to s. So the inverse tangent of infinity is equal to pi over 2 minus inverse s tangent. Pi over 2 radian minus inverse s tangent. And according to trigonometric relations, this would change to inverse s cotangent. And inverse s cotangent is equal to inverse 1 over s tangent. This video is already finished. To conclude, I hope it was practical and useful for you.